Hello, welcome to COMP9417, Machine Learning and Data Mining for 2020, the second trimester. So this will be my pre-recorded tutorial for week 2, and this will be how I'll be presenting my tutorials for the rest of the trimester. So what will happen is I'll have this pre-recorded tutorial where I'll run through the content of the previous weeks covered by Dr. Bain, as well as the tutorial questions and the Jupyter notebook for the relevant week. So they'll be uploaded before the Monday, which is my first tutorial in the week. And the tutorial sessions you're enrolled in, so I'm looking after Monday 6 to 7 p.m., Monday 7 to 8 p.m., as well as Thursday 7 to 8 p.m. Those times will be consult hours. You can think of it as office hours. So I'll be available on Microsoft Teams to answer your questions one-on-one. But they'll be a bit more interactive. So what I would recommend is for you to watch the pre-recorded videos before attending the tutorials, because I'll go through a lot of the things in depth. And then if you have any questions or additional things you're uncertain about, definitely attend the consult sessions, which will be via Microsoft Teams. I'll send a link out to everyone in my respective, tutorials before the tutorial starts. So you can just click on the link and I'll be using Microsoft Teams, and I think a lot of the other tutors will be using Microsoft Teams as well. So make sure you have that installed and up and running. So I'm going to restrict my Microsoft Teams consult sessions for Microsoft Teams accounts with UNSW. Now this is to prevent, I suppose, people outside of the course, who shouldn't really be here, from just dropping in and potentially disrupting the tutorial. So you'll need to log in using your at ad.unsw.edu account in order to access or join the consult sessions. Cool. So as I said, welcome. So I apologize on behalf of UNSW for the disruptions due to the whole COVID-19 situation. So everything's going to be online for this trimester. So we'll see how things go. Last trimester I was tutoring this course as well, and we transitioned maybe 2/3 of the way through the trimester. I think it worked out all right in the end. But yeah, look, I appreciate your understanding, bearing with us in this I suppose in some ways unprecedented situation. So a couple of things I want to talk about first. So I have set up a mini, I suppose, that thing disappeared. Sorry, let me just pull myself back up. I've set up a mini, I suppose, course website just for the students in my tutorial. And just the purpose of this is just to organize things, so there'll be all my emails here, contact details. Every week there'll be an overview of what was covered. The link to the slides I'll be using for this pre-recorded tutorial session will be up there. I'll also upload a link via YouTube of the pre-recorded tutorial videos, as well as the links to access the Microsoft Teams for the consult sessions. And I'll be doing this every week. There'll also be some interesting readings with things I find interesting as well here. I'll also email everyone in my tutorials with I suppose the Microsoft Teams consult sessions. But having everything all in one place might make your life a bit easier. So the URL was just andrewlauactuary.com and then /comp9417, just a little I suppose mini site for people in my tutorial. And again, you can click on that link to download the slides I'll be going through today. Cool. So actually one other interesting thing here is, so we'll be using Python throughout this course. We're going to assume that either you are familiar with Python or you have a decent level of experience, or you have experience programming and can pick it up on the fly. If you've never used if you've never used Python before, I implore you just get on it. I think it's a nice language. It's in my opinion, one of the easier languages to learn. So I suggest, if you haven't used Python, get on it. I've got a little crash course I made a while back in my spare time. This just covers a lot of the basic, I suppose, syntax. It does assume you have some prior coding experience. So it goes to control structures, some data structures like lists, tuples, dictionaries, etc., etc. But of course, there's a lot of good Python tutorials online that you can also use. I stress that what I put here, it's just for your interest. It's not necessarily, it's not an official list of readings. They're not prescribed. If you want the official list of prescribed readings, please refer to the COMP9417 course outline. Again, this is just, I suppose, extra material, purely optional if you are interested, just for your interest. Cool. So with that out of the way, I will get started. Let me move this into reading view. Cool. Sorry. So my name's Andrew Lau. Just a bit about myself. I'm an actuary by trade. So in my undergrad, I did a statistics degree and also actuarial studies. I also had a finance major as well. Then went into the workforce, worked for EY for a bit, finished off my actuarial qualifications, and decided to go back to uni to study some computer science. And I'm loving it a lot. Tutoring COMP9417 now, I suppose, as well. Here's my email if you need to contact me. The policy is, if you have a question, try to bring it to the, I suppose, Microsoft Teams consult sessions. It probably will be a bit easier for us to talk and for me to answer your questions if we can chat face to face, or at least if you can see my face and I can just talk to you. And if not, direct them towards the course forum. The logic being that if you have a question or uncertainty, likely many other students will. So it's a good learning experience for other students as well as it won't double up on, I suppose, questions being answered multiple times. So and then again I stress, so the slides here, they're pulled from COMP9417 from various trimesters, this trimester and previous ones. But I do stress that you use the official course outline lecture slide. That is the source of truth as to what is examinable. The slides I make here, it's a supplementary. It's to help me just give you an overview of what's going on in the course. Cool. So let's start off with an overview of machine learning. So this may or may not be your first exposure to machine learning. A couple of different things that we'll talk about. So when we think about machine learning, there's a few different types of data that I suppose can feed into it. Tabular data might be one that is, I suppose, maybe easier to understand, and at least for me, it's the one I'm most familiar with. So tabular data, typically, you have each row is an observation, or I suppose a training example, and then each column, going across each column will be a feature. And I'm just gonna take a moment here to sort of talk about a bit of terminology. So there's a few words being thrown about, but again, talking about tabular data. So you can think of, maybe I should pull up an example data set actually, just so I can speak to something. Otherwise, maybe it's a bit harder to. Here we go. For you to understand. Yeah. So this is a classic example of some tabular data. So each row going down, is an observation or a training example. So again, if you come from a statistics background, you'll notice that maybe the terminology is slightly different to what might be used in say machine learning land, but they're quite equivalent. And then going across, you could call these, I suppose, columns or features or predictors. It's just something, I suppose, which is an attribute of each of the training examples or observations. And then so typically you I suppose in supervised learning, which I'll talk a bit about in a moment, you'll have something called a target or a response variable, or dependent variable, right? There's a lot of different names. They're all relatively interchangeable. The machine learning would typically tend to say target for the response and maybe features instead of independent variables or covariates or predictors. Again, they're all largely interchangeable. So at least in this case, so let me talk about the target. So the target is I suppose something you're interested in. The column that you're interested in, I suppose, predicting or finding some relationship between the predictors or the features and that target. So this is this week's tutorial. And in this case, the target is it blood pressure? I think it was blood pressure, wasn't I? Let me have a look at this. Is it Pima India? Oh, it's a diabetes. We'll go through this in a bit, but I think it was blood pressure. What was the target? Let's have a look. Diabetes.target. Which one's that? Doesn't really help me out. 151. Where is the target here? BMI, or is it saved as something separate? Oh no, the target hasn't been saved in that data frame. It's sitting as somewhere separate. Yeah, sorry. So in that particular table I showed you, they were all features. But going back to this example here, in your tabular data, you might have another column here, say some measure of diabetes in this case, and that would be the target or the response is I suppose what you're interested in. Interested in potentially predicting, given let's say you had a new I suppose observation and you wanted to, I don't know, predict maybe the propensity, the likelihood of having diabetes. It's a thing you're interested in. Cool. So that's tabular data. And you can also have unstructured data. So we don't go into it in too much detail in this course. Largely it'll be tabular data. You can have a variety of things. You can have image recognition problems. You can have image data, audio data, a whole variety of different data. Now, I touched a bit on supervised and unsupervised learning earlier. So supervised learning just means there's a target, right? It's labeled. That's another loosely interchangeable term. So target, label, response, dependent variable. You can call it whatever you like, I suppose. We tend to use target here, I suppose, in machine learning and this course. But yeah, so that it's been labeled. The thing that you're interested in, what column it is, what feature, what column it is that you're interested in, and it's been labeled. It's known, right? And within supervised learning, you can think of it in terms of classification and regression. Okay, we'll talk a bit more about these later on. But in a nutshell, classification is when your target is, I suppose, it's categorical. An example might be you're trying to predict. This might appear in a few weeks from now. You're trying to predict, say, the type of fish, the species of fish based on some features. So it's categorical. Or you can have a model that predicts the let's say the click-through rate. When I say click-through rate, I don't know. Let's say you have a search engine and there's a bunch of links you could click on, right? And whether you click on it or not, right? I suppose maybe you can think of it as binary classification, whether something happens or not. Other examples are, so I mean, I work in insurance pricing, so we could have some tabular data, which is full of, I suppose, policyholders, right? And we're trying to predict whether they're going to make an insurance claim or not. So in that sense, it's a 0-1 binary. So you could think of that as a classification exercise. So regression, it's when the target is, I suppose you can think of it as numeric. It could be along the real number line somewhere potentially. So this could be, say, again, going back to the insurance example, you're trying to predict the claim size. So it could, of an insurance claim. So let's say it's motor insurance, right? And we're trying to predict, okay, what will the size of the claim be? It's going to be $500, $1,000, $2,000. It's not categorical. It's numeric. This lives on the, I suppose, positive real numbers. Well, not all the real numbers, given that it's going to be to the nearest, I suppose, cent or 5 cents. But you get the idea. Then we have unsupervised learning. So this is when there's no target, and you could and there's a variety of different ways we can use this. You could be using it to try and find patterns within the data. You could use it to I guess as a bit of clustering, to find groupings in the data. You could use it to find not just clustering. There's something called a principal component analysis, which we will see later on, which will, I guess, break down the data set into I guess you could think of it as things which dimensions which I suppose describe the data the best in a way, or explains dimensions which explain the variance in the data the best. But the key thing to keep in mind is that there's no target. Okay. So in a typical machine learning problem, this isn't the only way to go about doing it, but a typical structure will be something like this. So what will happen is, you have a whole bunch of data. It could come from a variety of sources, and you're gonna have to clean it up. You're gonna have to. There's a whole bunch of data cleaning and pre-processing that might come to play. For example, if you're piecing together data sets from various sources, they could be coming from various data warehouses and various sources. You might have to do a bunch of joins, left joins, inner joins, various joins to sort of piece it together. There might also be some dirty data, like there could be missing data which you might have to deal with, like say missing data imputation, and there could be other things as well. There could be typos in the data. You may also want to let's say you have a feature which is categorical, and you might want to group them together for various reasons. Maybe that particular feature, categorical feature, has hundreds and hundreds of levels, way too many levels, and you can apply a bit of your judgment or subject matter expertise to group them together, and that could end up being a feature engineering exercise, which I'll talk about in a bit. So one example I can think of here is, let's say you have I guess the make of a car, right? Maybe the feature is make of car, so you could have, say, Toyota, Subaru, Nissan, BMW, Mercedes-Benz, Honda, Holden, what have you, and you could potentially group it into, let's say, country of origin. So you could put all the Japanese manufacturers or the Japanese brands together, maybe put all the German brands together, etc., etc. And that could be a form of data cleaning, or you could leave both the features there, and you've engineered a feature, and you could sort of test it out and see which one is more predictive. So there's a lot of things that can happen in data processing and wrangling. There's an old adage, garbage in, garbage out. So you got to make sure it's quite good, the data going in, right? And then there's feature engineering, extraction, selection, so feature engineering is, I suppose, it's creating new features out of the raw columns or data you have. So let's say you have a model. Let's say you have a model and it's something to do with cars, right? And each row is some sort of car, right? And you might have a column which is power in kilowatts, say, or horsepower if you're American. But let's go with kilowatts. And then you have another column which is weight, let's say in kilograms or tons, right? You could create power to weight ratio, right? And that could be predictive for a variety of different things. So that's an example of an engineered feature. It's when you just create new features based on the raw data. You can be very, very creative here. There's a lot of things you can do. So let's say you're playing around with geographic data, and let's say each row you have the longitude and latitude of I don't know, say people. Maybe each observation is a person. You have the longitude and latitude of their dress. And an engineered feature could be distance to the coastline. You could play around with a bit of geometry. You could just draw some straight lines around Australia, distance to the coastline, right? You could do, distance to postcode centroids. You could calculate the weighted, the average longitude latitude of each postcode, based on weighted by a number of addresses, and then you've got the distance from it. That's another engineered feature. There's a lot you can do, really, here. And arguably, this can add the most value for tabular data in terms of improving model performance, right? And then you do that, and then you'll fit a bunch of models. You want to choose the right class of models for one. So you want to work out whether it's a classification or regression problem, and then when you do, you choose an appropriate one, and you could apply a bit of judgment. You could have a bit of a think about how the models work. Let's say it's a classification problem. Do you want to use naive Bayes? Do you want to use some sort of gradient boosting machine? Do you want to use logistic regression? Do you want to use k-nearest neighbors? Do you want to use a random forest classifier? There's a lot you can have to think about. Or do you even want to chuck a neural network at it, or a support vector machine, a classifier? There's a lot. There's a lot you can think about, right? And it could even be a case of, experience, that this kind of data, maybe for some reason one kind of model works a bit better, or you could just try them all, just fit a whole bunch of models and see which comes out on top, run a bunch of experiments in a ways, right? And then you do your model evaluation and your tuning, right? And when I say model evaluation, you typically choose some sort of performance metric, and say, there's a whole lot, and we'll talk about it later in the course, but say on the classification side, it could be, say, accuracy, which is just a percentage of observations you've predicted correctly. There's something called an F-score. You can look at Gini coefficients. You could look at log loss, entropy. There's a lot that can be done for that. And the regression side, and again, we'll go into details later, but I'm just giving, seeding the names into your head, so maybe they're in the back of your head somewhere. Regression side could be root mean square error, mean square error. You could even use, not the Gini coefficient, but you can use a Lorenz curve and the area under that. What's that score called? Yeah, there's a whole host of different scores we can use, and the one which you decide on, could depend on your application, right? Cool. And then there's an iterative process. So you do this, but you don't just fit like one model and call it a day. Likely, well, you might if you want something quick and dirty. But typically you want to iterate, and you try and improve on your model. You create some new features. Maybe you toss out the features that were a bit rubbish, the ones that weren't predictive. That's called feature selection. You distill it down to the features that you want. You could test out a whole bunch of different things. There's something you could try, forcing some of the features to be monotonically increasing or decreasing. You could you use an offset. Let me know if you want to know more about that. But we don't talk about it in this course. But there's a lot you could do to try and improve the performance. In terms of feature engineering and selection. And you refit the model and have a look and see if it improves it. There's some considerations here, like cross-validation or training and validation and holdout testing. But we'll talk about that later in the course. And then you deploy it and monitor it. You could just have a look, diagnostics, and you see if there's a model drift, or see if the model is not performing as well as it should. And then you might want to refine your models, or it could be an online model which is constantly being refreshed. Depends on the application, right? Cool. Linear regression. So this is the first, or linear model. This is the first, I suppose, machine learning model that we talk about in this course. Now I say machine learning model, but really it came from statistics, right? And there are, I suppose, there's a machine learning flavor to it, e.g., your lasso and your ridge regression, which I'll talk about later today. But I think it was Sir Francis Galton who first looked at this, and it was trying to predict the heights of children based on the parents' heights. So Francis Galton, I don't know if it was a biologist or statistician or something. Anyway, but this came from statistics, and in a nutshell, what you're trying to do is you're trying to fit a straight line to the data, right? I guess the line of best fit, which then raises the question: what is a line of best fit? Well, we'll talk about that in a moment. But yeah, you can see here, right, in this toy data set, on the x-axis is a feature. So this is just a one feature, univariate one fit. There's only one feature here. And this could be, let's say it's height, right? And on the y-axis, that's your target. It's your dependent variable. It's your response, right? It's something. It's what you care about, right? And based on your predictor or your feature, you're trying to work out, you're trying to fit a model, of say height, based on weight. Although in reality, height and weight it's more of a square relationship. It's not linear. Hence, I don't know if you've heard of BMI and body mass index, but it's what is it? Weight divided by height squared. So it's not necessarily a linear relationship. But anyways, let's just assume it's a linear relationship here. Right. So if you're trying to fit a model, and you want to fit a model because let's say you have someone new coming in, right? Let's say you have a new observation coming in. Let's say let me doodle on this. I think it's this one, isn't it? Yeah. Let's say you have a new observation, and someone comes in with height. Let's call it 175 centimeters, and then you're like, okay. I don't know how much they weigh. Let's put it into my regression model and boom, we work out that they weigh, say, 70. I apologize, I'm drawing with a mouse, so it is a bit cumbersome. and then so our model would say it's 70 kilograms, right? And so, yeah, so the point of this model could be that, you want it so that if someone new comes in, if an unseen data point comes in, you can throw a prediction. This is a prediction. So you'll see a hat here and there in this course. Hat, it just means I guess estimator. And why is it estimated? Because y is it's the actual target, right? But we don't know what it is. Maybe we do later when we measure it. But let's say he comes in has 175 centimeters. We haven't weighed him. We don't know what it is, so we estimate with a y hat. We estimate what their weight is based on their height. Right. Cool. And it might not even be for just predicting new points. It could just be useful. You're just interested in the relationship between the two for some reason. Cool. There's some interesting questions that come up when we think about all this, which we'll go into in a little bit. Cool. Right. So yeah. So fitting a linear regression is fitting a line of best fit, or could be a line of best fit. So, it's really fitting line of best fit. Sorry, I don't know why that's it should be blue. There we go. Fitting the line, or I suppose plane / hyperplane of best fit. Now, it's a line when you only have one feature, but you can imagine, right? You can imagine, right, if you had like more than one feature. Let me see if I can do this in a nice way with the mouse. Yeah, but you can imagine if you had more than one feature. So let's say, again, going back to our example with the predicting the weight. So let's say feature one is, I'm going to call it weight, right? And then this is oh, sorry, it was height, wasn't it? Height. Let's try a bit of cursive. There we go. Height, and and then this is your response variable. Let's call it weight. Now, if you only have two features, right? Then the line of best fit, will be a line, right? Something like this maybe, and you got data points like this. But if we have another variable, another feature. Let's call it x2, the second feature, and maybe it's waist circumference, right? That's another good predictor of how heavy someone's going to be. I think waist. I'm just going to go cm, just a bit easier, right? And then let's say you have a bunch of data points, and you're going to have to use your imagination here. Sorry, it's a bit messy. Yeah. But you're gonna have to use your imagination a touch here because I can't. It's hard for me to draw in 3D. But then what will happen is you don't have a line of best fit. Now you actually have a plane of best fit, right? So now this is a plane, right? And of course so your prediction will lie in this plane of best fit. And then if you generalize that to more dimensions, you hyperplane. That's linear regression in a nutshell. Line, plane, hyperplane of best fit. Now notation. So notation wise, sorry, I'm in drawing mode. Yeah, notation wise, you might see in a couple of different ways. You may see theta, you may see W, you may see B, you may see beta. I think in lecture one we see a lot of it as beta or B, if I'm not mistaken. But then in the tutorials it's W. Anyways, just keep in the back of the mind they may be used. You might see it in some places as theta. You might see it in other places as W or B or beta. But yeah, so Y is our target and our model is this. Y is going to be, this is called the intercept term. The intercept term plus, and then it's a linear combination. You got your feature multiplied by the first coefficient, and then the second feature multiplied by the second coefficient, all the way up to n many or m many features depending on your data set. Now, apologize if this notation isn't consistent with the lecture slides, but here I'm just going with n many features. This is the random error term, right? So in our model, we assume that the target is going to obey this function plus a bit of noise, right? These are all deterministic, you could say, and this is the only random point. So in our model, what we say is we have a deterministic relationship between, say, weight and height, but then we scatter a bit of noise everywhere, right? There's noise. There's noise. This is noise, right? There's noise. There's noise being scattered around. This is the epsilon, the noise, right? And it could be from a variety of different things. Measurement error, could be data errors, right? Could be a whole bunch of things. Could be maybe just have it. Maybe your model is just some of you haven't modeled. Maybe your model is too simple. It's not good enough. Anyways, so that's an error term at the end. And bear in mind. Yep, sorry, still in drawing mode. Bear in mind, you could see it, in vector form as well. Vector notation, you could either be an arrow at the top. Sometimes it's just bolded, or sometimes it's sort of implicit. It's not even bolded. But I think linear algebra is a prereq for this course. You should be somewhat familiar with. You should have seen this notation somewhere, either the arrow on top to indicate vector, or if it's bolded, or if it's in some ways implicit. Cool. And the X is the feature. Right. And in here the subscript represents the the feature number, and the superscript represents the observation number. So this will be the ith observation, right? And then this is feature 1, feature 2, and then you have the respective coefficients for each of them. Our prediction is just this. And again, notice the hats the hat notation tells us it's an estimator. Our estimate of the the target is made up of we're estimating the linear regression parameters. So you should be familiar with notation, I guess fully expanded out like this, but also you should be familiar with notation in vector notation, and later on maybe some matrix notation as well. But if you expand out, these are the same. So if you take this guy here is, I suppose, the column vector of all your linear regression coefficients, and we transpose it. So now this is a row vector of your linear regression coefficients, and you multiply that out by, I suppose, your features. That's going to end up being the same as this one here, right? You can also express in the dot product a variety of different ways. It's really just mathematical notation to make things easier in some ways for us when we write things out. Next thing I want to talk about, so what do we mean by best fit? I mean, it's all well and good to be hand waving and say, okay, yeah, like this is the line of best fit. It looks good to us, and maybe we have an intuitive sense of what kind of looks good from a human point of view. We look at it visually. Yeah, that feels about right. It's kind of in the middle. But we can't tell that to a computer, right? We can't tell it to an algorithm. Yeah, just fit a line that looks good. You can tell that to say your friend, a human, hopefully. and then we'll work it out. But we'll have to be a bit more, I suppose, specific, quantitative about what we mean by best fit, right? So one way to define your best fit is, and this should make intuitive sense. We're trying to minimize the distance between, I suppose, the line and all our data points. So you see all these purple, all the purple, I suppose, lines I've drawn here. That's the wrong direction, isn't it? So these are the distances. So this is effectively, what is it? I mean, it could go either way. Y hat minus y, right? Or you do the other way around. I mean, we square it either way, so it doesn't make a difference. But I mean, yeah. So this distance here, I'm just going to take the norm just to so it's positive. Yeah. So these purple lines here, that's the distance from your y hat to your y, right? And it should make sense. You kind of want to minimize this, right? But actually, what we look at is we look at the sum squared error, right? So it's not the absolute value. We look at the error, and the error is the difference between and then this is for the ith observation, is the difference between the prediction and the actual value. And sum square error, so we want to sum it all up across all your observations. This is our SSE, right? There's some reasons why we want square. I mean, you could argue, like why don't I look at what is it? Some, let's say, absolute error maybe. You could make the argument that why do I want to square it? What's the point of that? Why don't I just use this? Why do I have to square it? Yeah. So there's a couple of things between these two. So this one, the SSE actually has a nice, I guess, probabilistic interpretation, and we'll talk about it in a bit. But it actually turns out that if you minimize the sum square error, it's got the nice interpretation that it's also the maximum likelihood estimator. Assuming that these errors here, are normally distributed, right? So that's got that really, really nice interpretation. The other interesting thing about the sum square error is the sum square error versus the mean square error. I don't know why it's defaulting to white. It's a bit odd, isn't it? Sum square error tends to, I suppose, penalize outliers more. And why is that? Well, we're squaring it, right? So if you have a point which is sitting far out, let's say you have a point that's sitting far out, here, right? Now this outlier, well, maybe that's not much of an outlier. Let's say I have a point that's here, that's an outlier, right? And this point here, if you look at the distance, right, from the y to the y hat, so the y sitting here, and the y hat is sitting here, and you look at that distance, right? The sum square error, you square it, that's going to blow it up, right? Compared to you just take the absolute value, right? So that's another interesting thing about the sum square. But one good thing about this is, it's got that nice probabilistic interpretation. Cool. So that's what we mean by, I suppose, best fit. How to define what does make a line good. Yep. Cool. And then I touched on maximum likelihood estimation. So what is maximum likelihood estimation? In a nutshell, what it is you apply you make some distributional assumptions, right? In this case, for linear regression, we assume everything's normally distributed. Given a set of features, and the question becomes, okay, what is the most likely, set of features given my observations, right? So you express, the likelihood of seeing, your likelihood of seeing your observations as a function of your parameters, and then you maximize the likelihood of seeing that, right? So it's got that nice probabilistic, classical statistical perspective. So that is another way, but it turns out actually they're the same. when if you look at the mass and you look at what you're optimizing, you find out actually that if you're maximizing the likelihood versus minimizing the sum square error, you end up at the same solution, right? Which is, again, to me, which is a nice thing about the sum square error. It's got that nice, statistical, I guess, interpretation, right? And this is all well and good, and now we know how to do it. There's actually a couple of different ways to actually calculate, right, the coefficients. So we know in theory, what the coefficients should be, right? So we now we have a bit of theory about, how to define the line of best fit. We use, say, sum square error, and then we have, a way to work out, okay, cool, what should my, say, y-intercept, and what should my gradient term be, right? So my y-intercept, I'm going to use theta notation, and then the gradient would be theta 1 here. Just y equals mx plus b, right? Rise over run. Now, there's two different ways, as I said. You can use gradient descent. Hopefully you've seen that somewhere. So gradient descent effectively is you calculate the gradient, which is, I suppose, you think of the gradient as the vector of derivatives of the cost function with respect to all the various parameters, or I suppose coefficients. Put it another way, what is the LaTeX one for the upside down delta? No, that's not right, is it? Maybe I'll draw it out. Move this first. All right, so you have, let's say, a gradient, and that's going to be equal to, and what you do is you have your cost function. I'm going to just call it C, right? And then your first, I suppose, parameter, and then you do the same thing with your second parameter. Dot, 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 and then I'm just going to be a bit consistent with my notation. Let's say you have n features. Well, maybe it's n plus 1. Maybe it's n minus 1 then, because this, we're indexing at 0. And then you have a column vector of your partials on your cost function with respect to all your features. So this here is our gradient, and so keep in mind what we're trying to do here. We're trying to minimize something, and what that something is, we're trying to minimize the distance from your line of best fit to all your data points. So we want to minimize it. So what you do is you get your gradient, right, and you take a step in the opposite direction, right? Now, why is it in the opposite direction? Now you can imagine here, let's say, let's say we just have one feature. Let's ignore the intercept term. Let's just say this is our model, and we only have one theta or one parameter to deal with, and then this is our, I suppose, our cost function, and we have our gradient. We have our gradient here. The gradient vector is pointing this a ways. We're trying to minimize it, so actually we want to take a step in the opposite direction, right? So typically, you'd update your update rule. Let's say here, sorry, maybe I'll write it out. It's a bit messy, isn't it? Can I just do this? I'm not going to insert a text box. Sorry, I'm just saving. Yep. So what you typically want to do in your gradient descent is, let's say you have your theta 1, right? And then you reassign it, or you update it. You go theta 1, and again you want to take a step in the opposite direction, right? And the reason, because you look at this, the gradient is pointing up. It's telling you where you're ascending, but we want to use gradient descent. We're trying to minimize the C, the cost, right? So we take a step in the opposite direction. I'll talk about eta in a bit. And then you have your derivative partial C, and then partial what is it, theta 1. And so you want to take a step in the opposite direction, and you also need that feature there, don't you? Yeah, So that's gradient descent. We'll talk about it a bit more, and this is just for the one observation. There's some more details here which we'll cover a bit later, because you want to calculate it across the whole data set. But the gist is we're moving in the opposite direction of the gradient, right? Now that's one way to do about it, to go about working out the I suppose the linear regression coefficients. There's some advantages to gradient descent. It can be much faster than the second way. The second way is using the normal equations. So if you do a bit of linear algebra, you play around with a bit, you actually end up with this expression. You can actually express your linear regression coefficients like this, and involves some matrix inversion. And one of the problems with that is when you have a lot of features and your matrix gets quite big, matrix inversion can be computationally quite costly. So maybe if you have a data set of a few million rows and you have a few hundred columns, it can be quite costly, and gradient descent can be significantly quicker, right? But either way, the idea behind this is you want to minimize it, and one thing I want to tell you is linear regression. It's a convex optimization problem. You basically want to find the stationary point. I suppose here. You want to find the point when the derivative with respect to all the coefficients is 0, e.g. it's flat, and then you're at the minimum. Cool. What's next? How do we interpret the coefficients? So here is our linear regression model, right? And what does this mean? What is this? What is this theta 1? What does it all mean? The interpretation for this is, so one unit change in this guy, in say feature 1, will result in theta 1 change to the predictor. So here's a real life example, made up real life example. Let's say our predictor, our target is weight in kilograms, and our regression coefficient, let's say there's no theta 0 here. Our regression coefficient is 22. The interpretation here is, for every 1 unit change in height measured in meters squared, this is really x1. For every unit change in your feature, your weight goes up by 22 kilograms. Right. Okay. Cool. So the next thing we'll talk about is regularization. So I suppose, as I say, linear regression comes from stats land in a ways, but the machine learning, I suppose, flair to linear regression is this stuff here. It's regularization. It's a way to automatically, I suppose, select features, right? And to me, that's one of the differences between your traditional stats and machine learning. In traditional statistics, often you apply a bit more judgment. You might fit it by hand. Requires more, I suppose, at least maybe a basic understanding of statistical tests and how to interpret the diagnostics that come out of it. And you can apply a bit more control to the model you fit. But machine learning, tends to do away with a little bit of that. But of course you have a lot more data, and as one of the things is data is king, right? The more data you have, you can beat out a better model if you just have more data, right? So back to what I'm saying. So the machine learning flair to linear regression is this regularization term. Effectively what it does is it helps you distill down the feature subset. It helps you work out what features you want to use. Normally without regularization, you might do a bunch of statistical tests. You might do some forward and backwards feature selection to work out what you want to fit. You might even try fitting different shapes. You might fit x squared, x cubed, splines, various things. This is not part of the course, by the way. But yeah, so regularization, what it is it's a penalty for overfitting, right? Because one of the problems of linear regression, if you apply it just blindly, is if you chuck all the factors in there, you're going to overfit, and that's something we'll talk about in a bit. But overfitting, you're going to fit a lot of factors which maybe have no relationship to the target. They're useless. They're nuisance predictors, and that does nothing, right? The only thing it does is it reduces model performance because it increases the variance of your model without increasing any predictive, capability. So you want to control for that. And this is what it does. So this term at the beginning, this guy here, I'm sorry, the term at the beginning, this one here, that's your original, this is your sum squared error, right? And this is the original stuff. The new part of all this, that doesn't look very good, does it? The new part of all this, I suppose, the regularization part of all this is here and here. You have this penalty term at the end, and let's break it down. What is it? This is for your lasso regression. This is just it's a sum of the absolute magnitudes, of all your coefficients, right? And it's penalizing big coefficients, right? So what you're minimizing is not just the error, but you're discouraging coefficients that are too big. You want less coefficients, right? The lambda there is your regularization parameter. The more the lambda you have, the more you penalize your coefficients, right? So the higher lambda, the simpler model this is going to try to create, and the lower the lambda, the less penalization, penalty, sorry, and the more complicated. You might create a more complicated model, right? Now, these are quite similar. The difference being is this is what's called a L1, and this is what's called a L1 regularization, and this is what's called a L2 regularization, and this is to do with, I suppose, the I think we'll talk a bit more about it in later lectures. But you have concepts like L1 and L2 distance, right? L2 distance is what we're used to. So x1 minus y1 squared plus x2 minus y2 squared. So this is what we're used to, the distance between, let's say, point x, point y. This is, I guess, a L2. Sorry. This is a L2 distance. The L1 version, you'd just be taking, I suppose, the absolute values, and you wouldn't be square rooting. Cool. But we'll talk about this more, I believe, in later lectures. The most important thing to note here is that this is the same as before. So this is the sum square error. Sorry. From before, but now there's an additional regularization term at the end. In practical terms, lasso regression, due to some geometric reasons, and you end up having, I suppose, when you use this for feature selection, when you add this penalty term, you often, maybe if you have 100 features, you might distill it down to, say, 20, depending on your regularization strength. Lasso regression, the feature is either in the model or not in the model due to some geometric reasons, which is there's a good explanation in Introduction to Statistical Learning, Chapter 3, by Hasty, Tripsharani, and Gareth. I'm sorry if I'm forgetting the author names, but Introduction to Statistical Learning, Chapter 3, there's a good explanation there if you're curious. Ridge regression tends to have all the features. It might just sort of converge towards zero if they're very they're not predictive. Then you have elastic net, which is kind of a best of both worlds. It combines the two to an extent. This I don't think this is in the course, but it is just an FYI. Cool. Sorry, how long have I been here? It's almost an hour, isn't it? I should move on to the tutorial questions. But just a final word about linear regression models. For me, I feel linear regression models are sometimes criticized for being too simple or maybe not powerful by some machine learning practitioners. You might see it here and there saying, "Oh, linear regression is such a basic, simple model. We've got these fancy decision trees and random forests and this and that." I just still want to defend it a bit. I mean, in those comparisons that I've seen, often they just fit a blind linear regression model, right? They don't look at any statistical tests. They don't look at t-tests. They don't look at chi-squared tests. They don't look at residuals. They don't actually fit it like they don't fit it they don't fit it as a statistician or maybe a biostatistician or someone in the field. And again, I'm not a statistician, but I do know that the way that they're fitting it in some of those examples, it's not really a fair comparison. If you chuck all the features on there just blindly, yeah, the model might be no good, right? You know, there's a lot more power within linear regression that is it's not fair, to just compare the simple blind, just chuck all the features into the model. Linear regression. And linear regression, it's used in a bunch of places. To my knowledge, a lot in biostatistics, and you need a lot of clinical trials in your medical journals. They fit lots of, there's a lot of experimental design that goes place there. There's a lot of ANOVA, analysis of variance, and linear regression. And the sample sizes are often smaller, and you need a bit of like statistical robustness to report those findings in, say, I don't know, the British Medical Journal, for example, or Nature. You need some of that statistical rigor, right? You need to report a p-value. You need more statistical rigor. So look, there is linear regression models. They have their place, Anyway, so this is extension. This isn't part of the course. I just thought I'd just put in my 2 cents about it. There's some like interesting things that you can build on in terms of linear regression models. Again, not in the course, but there's something called a GLM, a generalized linear model. And I put in a link on, I suppose, the tutorial website. There's a bunch of links here, actually. Here. Yeah, this is interesting. So this is, so I'm a pricing actuary, and so this talks a little bit about what we do. Yeah, and it talks and a GLM, or generalized linear model, you can think of it as an extension, a more flexible extension on top of your linear models. But they're very useful. I just thought I'd put in my 2 cents about that. Now let's actually move onto the tutorial questions. So it's broken up into 2 bits. You have your, I suppose, your revision, your revision questions, and then you have your actual Q, your questions. And then we'll move on to the Jupyter Notebook after all this. Okay, revision question 1. So it's really just making sure you can do partial differentiation. So I understand this is a master's course, so it might be, I don't know when the last time you did any calculus was. It could be last year, last semester, or 5 years ago. Who knows, right? Might be a good idea to brush up on some basic differentiation. We don't need super advanced calculus here in this course. Just know how to differentiate something, nothing too fancy. Yeah, but the key here is the trick here is with this partial differentiation. Just treat all the other variables as a constant and just differentiate normally. So for example, here you're calculating the partial df dx, or sorry, del f del x, right? And so you look at your first term, and okay, you see your x. Okay, so bring the 2 up, 2a1x to the power of 1, and then all the other variables, you treat them all as you treat them all as constants, right? So and then you have your y squared there, and you do the same for all the other guys. I shouldn't have to go into too much detail, but yeah, just treat the other variables as constant. Just remember that. Revise some basic calculus. It should be fine. Revision 2. Again, same sort of thing. I want to spend a bit more time on the, I suppose, more interesting stuff. This is just a revision of calculus. Revision 3. Yeah. So what this is it's using, I suppose, your derivatives or calculus to find an optimum, right? Be it minimum, maximum, and the reason for that is kind of explained here, right? Sorry. So in this example, you're given a function of x, and you want to find the minimum, and you want to find the optimum, and you want to work out if the optimum is a maximum or a minimum, right? Now, the way you go about doing it is, if you look at this graph, this is x here, and this is y. This is y as a function x. So you can see here that that when when it's flat, and this is gradient, when the gradient is flat, that's the minimum, right? And that's the key concept we use here to find the minimum. We want to find the point, not here, when maybe the gradient is, here is, I don't know, maybe it's like 3 or something, right? Right? And here it's 0. We want to find the point when the gradient is 0, right? And when the gradient is 0, we solve for that, and that should get us the some sort of optimum, right? So you differentiate it, you find the partial. Oh, there's not partial, you just differentiate it. I think this should be a d because this is a function of one variable, but maybe I'm just being pedantic. Anyways, you differentiate it, so it was 8x minus 3. You set this equal to 0, right? And then you rearrange, and x equals to 3 on 8. I think that's 3 on 8. And then the next question is it a minimum or a maximum? So the way you find that is you take the second derivative. If it's greater than 0, it's concave up. If it's less than 0, it's concave down. In this case, because it's greater than 0, it means it's concave up, and therefore it must be a minimum. Next question. What is the loss function for the linear regression? So the loss function we talked about earlier, sum square error, or mean square error, they're equivalent. I mean, we use mean square error here, but you minimize one, it's effectively the same. Minimize sum square error, mean square error. But yeah, the loss function, mean squared error, and you can see here what it is the error is the difference between your actual target value, and your predicted target value. You can change your order back and forth, doesn't really matter because you're squaring it. And this is the actual target value, and then this, maybe I should do it here. Sorry, this is a predicted target value. Cool. Oh, and this is just for I guess univar. I mean, you only have 2 parameters. You can extend this out to n many predictors, but this is just for a two parameter linear regression. Question 1. So this is I guess deriving what the linear regression parameters should be from scratch. So we have a simple linear regression model, and I say simple linear regression because this linear regression model is it only has 2 parameters. You have your W0 here, and then you have some sort of gradient. Was it rise over run? And that gradient here, that's your W1. So this is a simple linear regression of 2 parameters, and then you have, of course, your data points, whatever that may be, something. And you want to derive an expression for your 2 linear regression coefficients, the y-intercept and the rise over run, the gradient. Okay. And so how do we do this? Let me just jump over here. So effectively, what we're trying to do is we want to find the global minimum where the loss function, or the loss function, or the sum squared error is minimized. Now we have 2 variables here. We have our y-intercept, and then we have our I suppose our gradient of the straight line. And hopefully you can see in this diagram, and this is a classic bold concave up convex optimization problem, the point at which it is a minimum, and this is the global minimum, right? Is when the derivative, the partial derivative with respect to both parameters is indeed 0, right? So this guy here is 0, and this guy here is 0, and you just got to solve for that, right? So what do? We set up our optimization problem, the sum square error. The mean square error, right? And then we have to, well, our goal, remember, is to minimize this, right? And the way we minimize this is we need to set both the partial derivatives, del L, del W0, and del L, del W1 to 0. Okay, so let's do that. Now, we start off by calculating the partial derivative with respect, with the green here, with respect, oh sorry, the purple here, with respect to the intercept term, W0. Okay, yeah, so from here to here, we just bring the partial, I mean, this is not indexed with I, so we can just bring it inside. And then we just apply the chain rule. So you differentiate this, so the two comes to the front, right? And then you differentiate the inside with respect to W0, and it's negative, so negative 2. You rearrange it, and then you have this. Now at this point in time, and this is something which Omar Gaddis, the head tutor, he's changed the notation. I quite like this. So this is the bar notation. So you might be familiar with it. If you've ever seen this, X bar, it's the sample mean, if you've ever seen that. And yeah, so this is X bar, or sorry, this is sample mean, right? You just get all your X variables and take the average. So it's basically this concept, right? So this is Y bar here, is you take, you'll replace X's with Y there. You just take the average of all the Y's, right? And we use this notation just to clean it up, make it look a bit nicer, right? And then rearrange, and don't forget we set it to 0. And again, the reason we're setting it to 0 is because we want the partial derivative to be flat, and that's when the minimum occurs. And we'll have this expression here. One of the problems is our solution, or not solution, well, our expression for W0 has W1 in it, but we don't know what W1 is. Okay, so then we're not done yet. We need to calculate W1, the partial derivative the partial derivative of the cost function with respect to W1. Set that to 0, and then we have a system of 2 equations, and then we just solve, right? Okay, so we do that in this step here. So we apply the same, we do the same thing. So now we find the partial derivative of our cost function. So remember, this is your MSE. I might have accidentally used sum square error instead of MSE in the previous slide, so I apologize if I did. No, that looks fine. But just bear in mind, mean square error, it's just got the 1 on n in front of it because you're taking the average. And if you have no 1 on n, it's a sum square error. Okay. Right. So we do the same thing. This is our cost function. This is C, or I guess your MSE. You take the partial derivative with respect to W1. And looking through this, the only thing here which has W1 term is here. But yeah, so you apply the chain rule first. So you bring the 2 out, and then you differentiate inside, and that's here, so it's negative. So that becomes negative 2, xi, and all the other stuff just comes down. You rearrange. And so just bearing in mind, you only really need the capital sigma, the summation, when something is indexed subscript I. Otherwise, it doesn't really matter, right? So your first term, well, they bring the negative 2 out, and the first term is, you need 1 on n in front of everything. So 1 on n, sigma, and then what is this? So it's xi, yi, and they're both subscript I, so it's got to have the sigma there. The second term, is it W0? There's no x's. Oh, well, there's that x there. But this is not subscript I, so you can bring it out. The last term, the W1, you can bring it out because it's not subscript I, but this is subscript I, so you can leave that there. But then that's multiplied through, so it's xi squared. Now you rearrange it, and you apply the bar notation that I discussed in the previous slide. You set it to 0, and then when you set it to 0, you have this expression here. And then effectively you have what? You have 2 unknown variables and 2 linear equations. Substitute and solve. So W1 is here, and the W1 is expressed in terms of W0. The rest are in a way constants. So all you have to do is you just got to sub in W1, and W1 is just this guy here. And remember, we found that out in the previous slide. Y bar minus W x bar. Y bar minus W x bar. So we just sub that in. And then we rearrange, and we have, I guess, our solution. W1 is equal to, well, this expression here. And then once you work out W1, you can just sub it into here, and you're done. Fantastic. Cool. The extension to this is we want to derive. So we talked a bit about ridge regression earlier, but we want to describe the supposed least squares estimates for your ridge regression. Now, the only thing different between the, actually, let me just make this a bit clearer. Just click that. Why is that? That's fine. Now, the difference between your ridge regression and your normal regression is this penalty parameter here, right? The lambda W1 squared. Now, if you follow through in the working, when you look at when you try to take the partial with respect to the first parameter, W1, the y-intercept term, you'll see here that this has in a way nothing to do with W1. It's a constant, so when you differentiate it, disappears, which basically means that the expression for W0 is exact same. So this here is the same as before. So it's the same as your regular regression. So same as your non-regularized linear regression. So I'm not going to go through this again. Now, on the other side, and when I say on the other side, I mean the other linear regression coefficient, W1. We do the same thing, and just bear in mind there's the addition of this term here, the ridge regression penalty parameter. So you just do your partial differentiation as before. Maybe I'll make this different color so you can kind of see. You do your partial differentiation as before, but then you have this extra guy at the end, right? And then you do the same as before. You set this to 0. You rearrange it, and this actually looks slightly different. So we've got that lambda term there. What did it look like before? If I can bring it up, it's W1, isn't it? Yeah, here we go. Yeah. So here is normal regression. There's no lambda there for the estimate of W1. Now we've got regularized regression. The only difference is we have this extra regression guy here. Same process. Now you have an expression for W1 in terms of W0. You have an expression for W0 in terms of W1. Substitute. So you perform your substitution and you land on this, right? So this is your solution for your second, your gradient term, your second linear regression coefficient. And then once you calculate this, you can sub it back into here. And that's ridge regression for 2-parameter linear regression. Great. The next question I want to talk about is, what is this? So this is applying what we've found in terms of the solutions, how to calculate the W0 and W1, the linear regression coefficients, to a real world, I suppose, a toy data example. Now, one interpretation of what we saw before in terms of the W1, this is the gradient term, is that you can think of it as the covariance between X and Y, and hopefully, I think there's a bit of stats revision in last week's lectures, but covariance, you can think of it as how much two variables, random variables, tend to move with each other. So if there's a strong positive covariance, as X goes up, Y tends to go up. And if this is a negative, strong negative covariance, then as as x goes up, y tends to go down, then opposite directions. Is just scaled by the variance of x. Right, now this is another alternative representation of W1. So you might recall just then we derived this expression. You can rearrange it and it becomes that. You can see my working here. Cool. So this is all well and good, but how do we actually apply this? Here's our toy data set, and this is the target. Yep. And then this is our lonely, I suppose, feature. And this is actually, I put it in Excel. This is what it looks like. Here's a table of data. You have your features and you have your target, and this is how you go about calculating it, right? So this is that formula we had from before, right? Now, how do we actually calculate this? What is XY bar? XY bar just means you're going to take the average of XY, right? And that's this, isn't it? This one here, 49.9. Right? So you just multiply XY across all your observations and you take your average. Remembering what X bar is. So this is how you calculate XY bar. Okay, and you do the same for all the other guys, and it should be reasonably reasonably clear as to how to go about calculating these things. Just follow my working here. Yeah, cool. And so you do that, and then you plug it into the formula, and this is the formula that we derived earlier, and then we find, okay, cool. What does our line actually look like? It looks something, so let me just change color again, just to make things a bit clearer. What does it look like? Our linear regression equation looks something like this. Looks something like this, maybe. So this is our target. This is our x value, right? Our y-intercept here is W1, but that's equal to -1, isn't it? And then our rise over run, our gradient, is 15. This is W0. W0 is -1, and our rise over 1 is run is 15. Sorry, I'm drawing with the mouse, so I'm trying my best here. I don't have one of those Wacom stylus. I don't have a stylus or a tablet thing, so this will have to do. Cool. Right, so that's one way to go about doing it. You can go through and follow the I suppose use the averages, and actually just to point out, this is a sample covariance. We talk a bit about the difference between a sample and an estimator and a sample something versus, I suppose, a true parameter. So something to keep in mind is that your mean and your sample mean, they're different. Sample mean is an estimator of the mean. In the same way, sample covariance is not covariance per se. It's the estimator of the covariance. And this happens to be the sample covariance. This is the sample variance. Sorry, this is not the sample variance because it needs a bias adjustment, but kind of like the sample variance. Cool. Population variance. It's still a sample. Yeah, we don't have to worry about the details too much here. Yes, that's one way. The other way we can go about doing it is, you might recall earlier on we talked about one way to find out the whatchamacalls, the regression coefficients. We can either use your gradient descent. You can find the you can set the partial to 0 and find the minimum. You can also express it in terms of a matrix. There's a matrix inversion there. You can solve it this way. That's what we go about. That's what we go about doing here. So this is the formula, and I think I wrote it up here as well. Where did I put it? This guy here. Just copy across. So these are the same. It's just they use W here instead of yeah. And the notation is probably a bit better because this should be an estimator. Maybe there should be a hat, but anyways, yeah, it's the same thing. So you take X, which is what we call the design matrix. Design matrix is just the matrix representation of the table of data without the targets. So each row is an observation and each column is a feature or a predictor. You get the transpose, multiply it by the design matrix. So the transpose of the design matrix multiplied. Actually, I take that back. The design matrix have features in it? Oh, it's a target. I forget. Design matrix. It doesn't have the target in it, does it? I'm just trying to remember. I feel like it doesn't. No, no, it doesn't. I was right. Cool. Yeah, it is a design matrix. You invert it, multiply it by the transpose of the design matrix, and then multiply it by the vector of the target, the actual target values, right? So you can do a couple of different ways. You can do it by hand, and then when it comes to matrix inversion, so this is our, you might recall from your calculus, first year calculus, sorry, not calculus, first year linear algebra. You got a little formula here for your 2x2 matrix inversion, or you can solve the system of linear equations, either or you can use Python. So NumPy or numerical Python has a way to calculate the matrix inversion. Where is it? Here it is. Invert. The invert function. Cool. So either or, and you'll find that you land at the same thing. So 15 -1. Oh, sorry. I realized I got it the wrong way around. Let me clean this up. This is wrong. It should be something more like this. Let's do this again. So I misread the subscript. So actually the gradient is 15, and then it's just -1. So it's here, W0, and it's at 15. Is it? Yeah, that's right. Gradient's -1, so I suppose rise over run. W1 is equal to -1. Rise of 1, and then this will be 15 because the gradient's -1. Cool. Let's move on to the Jupyter Notebook. Come on. There we go. Yes. Right. Let me zoom in a bit. Linear regression. As mentioned earlier, the stuff we'll be doing in this course is in Python. So arguably the two most common popular languages in the field of data science and machine learning are Python and R. They're both good. Python or R. They're both. I think they're both quite good. There's pros and cons of of using one or the other. R tends to be more popular with statisticians and also actuaries. I think a lot of it's maintained by stats guys. Python tends to be more popular, I suppose, with software engineers, software developers, and I guess more pure data science guys. But they're both good. They're the pros and cons. I like them both. Well, I actually prefer Python, but I think R has its own nice little things about it. But we'll be using Python here, so make sure you're familiar with Python. Cool. And within Python, there's some modules. Excuse me. There are some modules which are quite ubiquitous, and so you'd want to be familiar with your pandas. Pandas is, I suppose, the de facto tabular data module, and tabular data manipulation module. So make sure you're across that. NumPy, NumPy, a lot of pandas you can think of as a bunch of NumPy arrays stitched together, and NumPy forms a lot of NumPy is a required module if you want to use sklearn. Sklearn uses a lot of NumPy stuff. So make sure you're familiar with pandas, NumPy. It's got some nice matrix linear algebra stuff. But also it's a more efficient way to deal with and store data than the pandas. The NumPy arrays they're quite good. They're very fast. They're a lot faster than say your standard library lists. They're good. Cool. So what are we talking about here? We're going through a toy data set. So we have a diabetes data set. We have a diabetes data set, and there's 10 features, and the target is we're trying to predict their some measure of diabetes disease progression. I'm not a doctor. I don't know exactly what this is. All I know is the target something to do with diabetes. So in a typical data science or machine learning project, you want to do what's called exploratory data analysis or data exploration. In a nutshell, it's a whole bunch of plotting and understanding your data. This may or may not be feasible depending on the size of your data set. If you have like 1,000 features, you're probably not going to be plotting a lot of them. You might do some here and there. You could probably look at some summary statistics, maybe look at some key features, maybe look at the features which are the most highly correlated perhaps with your target. But yeah, it depends on your data set. So one thing we're trying to do here is we're trying to understand the target. So this is often quite good. There's a couple of different things that are good for this. It's also often good to understand the distribution of the target. You know, I mean, if say is the target distribution, is it normally distributed? Is it right skew, left skew? Is it bimodal? That could have an impact on the kind of model you might want to use, especially in regression land, where you do make a fairly explicit statistical. I mean, there is you can make an explicit statistical assumption in the sense that it's normally distributed. With something a bit more non-parametric, maybe when you go to decision tree land, maybe it could be less of a thing, but it's still good to understand the distribution of your target, your response. This is a box plot of the response. This is the maximum. This is the minimum. This is the 25th percentile or the first quartile. This is the median. This is the 75th percentile or the third quartile. It's a good kind of way to sort of understand it. It looks like there's a bit of a right skew here, maybe, if I'm not mistaken. We can confirm this. Yes, there's a bit of a right skew. How did I tell there's a right skew? Well, the maximum seemed to drag out. The maximum and the 75th percentile seem to be sort of skewed out to the right, so it looks like I might have a right skew. And now what we're doing here is we're doing some what we call one-way comparisons or one-way cuts. Why is it called one-way? We're just plotting the target. And one nice bit of exploratory data analysis is you look at the target and you look at the scatter plot of the target, a one-way comparison versus individual features. So you could have a hunch, or you might consult with some subject matter experts. In this case, maybe you talk to the clinicians, you talk to the doctors, you talk to the epidemiologists or whatever, maybe even the biostatisticians. And maybe the doctor's like, all right, we reckon BMI should have a very strong link with diabetes. And I'm pretty sure that's the case. And so maybe you test out a few of the features because you want to work out, okay, what do I want to fit? What do I care about? What features could be predictive? What might not be predictive? Have a look here. Hey, looks like there's a relationship here. Maybe there's something worth fitting. And you might want to chuck it in and see how it looks in the model. And this is all part of your exploratory data analysis. So this is one by one, maybe it's a bit manual. A way to sort of do it all at once is you use what's called a correlation heat map. So this basically allows you to look at correlations between all your features and your target all at the same time. Let's ignore the other ones for the time being. I think the most interesting one to look at right off the cuff is the other correlations between the target and the various features. So you have a look. It seems, and here red means positively correlated and blue means negatively correlated. You're looking for deep colors, right? Deep blue or deep red. What are the darkest colors here? BMI. So BMI is a positive correlation to the target, and it's a deeper level of redness. Blood pressure seems quite dark as well, actually. And what's this? I don't know what these are. There might be some measures of blood pressure or some other health indicators. I don't know, but something. So this, what does this tell us? This suggests to us that we might, in our model, we might want to fit BMI and blood pressure and maybe like, you know, S3 and some of these other indicators. Another thing which is quite useful is what's called a pair plot. The pair plot looks at this. It automatically plots all the I suppose the scatter plots of all your combinations of your columns, your features, and target all at once. So you can look at it all at once. So one other thing I should probably mention here is, not only does it look at the correlation between your target and your features, it looks at correlations between the features. Now this could be interesting for a variety of reasons. Now there's a concept called a correlated feature. Now that is to say when you have two features in your data set which are highly correlated. What's an example here? Maybe BMI and blood pressure. Actually, let's check that. Blood pressure and what is it? Oh, blood pressure and BMI. Yeah, these are all quite correlated. I mean, yeah, it seems somewhat correlated. I mean, to me, it feels like if you're heavier, you should have a higher blood pressure. But let's say there's even more correlated than here. Now, when you fit a regression model, typically you don't really want to fit correlated features. You know, if you have one, if let's say you have 5 features that are perfectly correlated, there's no point checking all 5 in. Maybe you want the one which I suppose maybe from a judgmental point of view makes the most sense, you know? Or you might want the one which seems to add the most uplift in terms of predictive power, or you could run a bunch of statistical tests. The problem with fitting a bunch of correlated variables is it increases the variance of your model, so it makes your model performance worse for no good reason. It doesn't add any predictive power, but it just adds variance to the model, which is not good. Ideally, you want the variable which seems to have a causal impact. Causality is difficult to establish, though. But you know, like this is an example where you could probably consult with some doctors, and maybe they could say, "Hey, no, we know there's a causal link between BMI and diabetes." You don't have to rely on your stats. You can talk to your doctor. They probably know some science and some biology or something. That it's not just correlated. There's a causal effect. But often causation is kind of hard, right? Cool. So you have all these pair plots, and you can see how any other features if they're correlated. And if you have heavily correlated features, you might want to examine just ditching one of them or the other one. You don't want both of them necessarily. Cool. So now we've done a bit of exploratory data analysis. Now we actually want to fit the model. So what's happening here is this is I suppose we're only fitting one feature. So we've only got the intercept term and the gradient term. You could, in theory, fit a linear regression model more terms. Just for simplicity here, we're just doing the one. And what you can do is, you're cycling through. So in this case, it's fitting feature number 2. Feature number 2 is, let me get rid of this guy, is 0, 1, 2. Again, you index at 0. So BMI. And it looks pretty good. You can also test out. Let's try sex, right? Let's see how it looks like, right? Just toss this out. I don't think I would fit that. You could run a t-test. You could run a chi-square test to be sure, or at least have a bit more statistical rigor. And I stress the stats here is not part of the course. It's just for FYI. It's just an FYI for you guys. You don't need to know about t-tests or ANOVA. But just looking at this, right, I don't see too much of a relationship between, say, male and female, or maybe a slight one. But if I had to choose, the BMI seemed pretty a much better model. One other thing you can do is just let's have a look at the scatter plot. This is the target, and let's have a look. Age doesn't seem to have much of a linear relationship. BMI seems pretty good. Blood pressure seems all right. S5 seems pretty good actually. Let's try S5. S5 is 0, 1, 2, 3, 4, 5, 6, 7, 8. So it's feature number 8. Let's try that. Yeah, that looks pretty good as well. Yeah, so that's one of the that's one of the useful things about exploratory data analysis. Can give you a bit of a guide as to what features you might want to fit. Now, of course, you don't just have to have just one feature; you can fit many of them. But in this Jupyter notebook, we're just doing the one. Cool. Next thing, training and test data split. Now, there's a concept called overfitting. Now, essentially, what overfitting is overfitting is when you pay too much attention to your training data set such that your model doesn't generalize well to a unseen data set. So we typically partition the data set off. You'd have your training. In the simplest case, you'd have your training data and you'd have your test data. So you do all your training and you're fitting your model, you're tweaking your model and your training. And then only in the end, you look at the test data set to give you an idea, hey, is the model any good? Will it perform well? Because it could be a case that, you overfit hard. You overfit hard to some training data, right? Like, oh, actually, no, sorry, I don't need to draw it's here, right? So let's say, it's too many, oh no, I'll draw one here, it's probably a bit easier. I'm sorry. Let's get rid of this guy, get rid of this guy. And let's say this is the BMI from before, and this is some sort of measure of diabetes. I don't know what, something. Then we have our data points. One here, one there, one there, one there, one there, one there, one there. Now, we fit. Let's fit one model. Something quite simple. Just two parameters. This is a two parameter model, and this could be, say, y is equal to model 1, two parameters. Could have another model, model 2. And maybe I should type this up. It looks pretty ugly, doesn't it? Theta 0 plus theta 1 and x1 plus theta 2 x2. We have several different models here. There's model 1, this is model 2, model 1 is the blue. Sorry, the teal maybe. Model 2 is the green. And then let's have that's a crazy model. I think you guys know where I'm going with this. Oops. Huh? Sorry. Drawing is hard. Yeah, you get the idea. Like, just imagine a model which is just has a crazy curve which just goes through everything, right? So there, model 3, and this just some ridiculous, right? Let's call it this one. Maybe it's got like 1, 2, 3, 2, 4, 6, 7. Maybe it's got 7 parameters. Now, the interesting thing about all this is, you'd also want to look at the I guess the sum square error, and the sum square of the train, as well as the validation, or maybe let's call it test. So the first one on the training, look, maybe it's got the maybe it's got the highest training error. So let's call it 1500. On the test set, let's call it 1750. right? Model 2, maybe something similar. Maybe it could be a touch better here, but maybe actually it's a touch worse. Maybe it's a touch worse here on the test data set. Let's try and make it green. Yep. Then we have our model 3. This is 0 training error. Sounds good, right? This is something you might see, and this is kind of, I'm trying to demonstrate the concept of overfitting here. So overfitting is when these black dots, they're the training data, right? And then let's say maybe I got maybe purple. This is the test data set. Now, maybe there's one point here. Yeah. Now the purple is a test data set, right? Now this red model here, which is overfit hard, which means it's paid the black. It's paid so much attention to the black dots, the training data set. It's fit to the noise, right? You could argue that the upper net it's noise. Maybe the true signal is maybe something like the green line or the blue line, right? But it's just fit to the noise. It's paid way too much attention to the training data. If the model's way too complicated, there shouldn't be 7 parameters. In this case, it's a bit of a joke example because I've got the same number of parameters as I do points, so you can have a perfect fit. And here you do, so you can see here that this is overfitting. You paid so much attention to the training data. There's very little noise. You just hugged it so closely, but then it's rubbish. It's a useless model because when you feed it a new data point, something else, it's no good. It's just absolutely off. So, what was I talking about? Back to here. Sorry. So this is I know it's a bit of a segue. So this is the concept of your training and test data set. The reason you do this is you want to split up your data set into like a test data set, a data set that the model has never seen before. Reason being, you want to see what the model will look like for unseen data. You want an indication of the performance if you were to actually deploy the model. It's very important to not let the model see the data at all during the training process. Otherwise, it's a bit like cheating. It's like seeing, you can think of a test data set like doing a uni test, and the model is a student. You want to work out which one of your students is the best, right? And so you let the students train on like some practice tests during the term, and then at the end of the trimester, say, you give them tests and you see which one does the best. Do you want the student which learn all, like, say, the multiple choice answers for the training test, the practice test, but just has no idea, just doesn't understand anything come test day? You don't want that student, right? You want the student that like it does pretty well in the practice test, but has also learned and formed the model in his head that can generalize to like new test questions. Analogy. Cool. So what's happening here is, here. So the blue dots are the training data set, and the red dots are the tests. And what you can do is you can look at the error on the training and the test data set. What happened here? They're there to run all. Yeah. There's So I'll let you play around with this, but the interesting thing here is what you can try doing is you can try playing around with different features, like try age, try sex, try BMI. Just try and work out which one's the best. Which one's the best model. You can test all of them out and just sort of see which one has the best mean square error, say, on the test data set, not on the validation set necessarily. The test data set, that's the gold standard, right? Doesn't matter if you do well in the training data set to an extent. I mean, ideally you want to do well in both, but the test data set is more important. Now, typical considerations are like when you do your training and test split, and it could depend on how much data you have, but it's quite typical to have, say, 70-80% of your data to train your model, and then you have 30 to 20% of the data to test the model. There's other ways to do it as well. If you have even more data, and it's quite common, you might use a training, validation, and then test split. So what you do is you partition your data into, I guess, training and validation, right? And you use that training and validation set to build the model. So you train the data on the training set, and you repeatedly test different models on the validation set, and then when you got your final model, one that you're happy with, then and only then you look at the final test set. That's even better than just training and test. You have another layer, right? What's even better is you use cross-validation in this process. The problem with cross-validation, though, is it's computationally intensive. You got to fit the model like many times. If you have, like, say, 6-fold CV, then you got to fit it 6 times. So it's about a trade-off. You got to consider how much data you have. You got to consider how much compute you have. You know, like, do you have a rubbish laptop that's not going to fit very well? Do you have a pretty good computer that you could use? Do you have access to cloud computing? Maybe you have access to AWS, Amazon Web Services, their Elastic Net, not Elastic, is it? It is Elastic Net, isn't it? Their is it called Elastic Net? That's the same as the regression, isn't it? Is that where they got the name? That just came to that realization. Elastic, because you have Elastic Net Regression, but then Amazon is also called Elastic Net, isn't it? Amazon AWS Elastic. Maybe that's why they call it Elastic Net. I don't know why. Huh. EC2 Elastic Net Cloud. Sorry, this isn't a plug for Amazon. You can use whatever cloud computing you want. No, Elastic Compute, not Elastic Net. Elastic Net's the regression model. I'm getting them mixed up. But anyways, yeah. So depending how you do it depends on your level of compute, how much compute you have available, how big your data set is. Gotta consider all that. Now, back to the lab. Yeah. So there's a couple of other different metrics you can use in terms of model performance. We looked at the mean square error, but the problem with mean square error, I find, is it's not intuitive. Like, if someone told you my model's really good, it's got a mean square error of 100,000, you're like, okay, cool. What does that mean? It's hard to interpret. R squared, R squared. This is something which has a nicer interpretation. The score generally lies between 0 and 1, and the closer to 1, the better the model, with a few caveats, I should say. But the R squared, the interpretation of this is it's a percentage of the variance in the data explained by a model. So it's how much you see, like, randomness in the data, how much of that the model explains, right? Again, there's some caveats there, and actually this applies to mean square error as well. R squared doesn't account for the number of features. There's a concept called parsimony, which basically means that you want the simplest model possible that can explain the data, right? That is consistent with the data. Occam's razor is related. It's related to Occam's razor, which says that the most likely hypothesis is the simplest one. You know, so you like, there's no reason complexity for the sake of complexity. There's no reason. If there's a model which performs equally well, or maybe just similar enough, but it's a lot simpler, you'd probably prefer the simpler one. R squared doesn't allow for that. There's something called adjusted R squared, which has a penalty term for more parameters. That's pretty good. Adjusted R squared. No, I want the Wikipedia article. There's that. It's got a penalty term, which just sort of allows for the fact that with your regression and the more parameters you add, the better the R squared, in a way. So adding parameters cannot decrease the R squared. So then, like, for example, in that silly toy example I made up, the R squared of this guy, that's fantastic, right? But again, this doesn't allow for overfit or parsimony or Occam's razor, none of that, right? The adjustment is, where's the adjusted ask? There it is. Yeah. So there's a penalty term here. P is a number of parameters, or the number of features you could give it as. Yeah. So there's that parameter. There's a lot to this. Your linear regression. I think it's pretty good. I think the GLM is quite interesting. I use GLMs a bit at work. in the insurance context. I think it's pretty good. So we might look at things like we'll have like a logistic regression model for claims frequency. How likely someone is to claim, and you might have like a claim size model. So given there's a claim, how big's the payout? Is it going to be a total loss? Your car is just destroyed. $50,000, say, maybe it's a Beamer or something, or it's just a scratch or something. I think they're pretty good. And there's something interesting as well. Interaction terms, again, not in the course. None of this is in the course, I stress. But interaction terms, that's something which is quite interesting actually. That's not really touched on too much in this course. Maybe it's more of a stats concept, but I do feel that if you do end up in some sort of I suppose data science sort of field, I think you should know about interaction terms. That concept, it is important, I think. Yeah. Anyways, so it's been almost 2 hours. So I'll leave you guys with that. This will be uploaded on YouTube in a bit. Link again the website for the site. So andrewactuary.com. Sorry, it seems a bit narcissistic. I apologize in advance. 9417. Go here. Upload. There's an overview. Overview of the topics covered. Link to the slides. There'll be a link to this video, and then I'll also post up a link to the Microsoft Teams consult session here, and some interesting readings. Again, not official, not part of the course, just for your curiosity. Thank you guys. Have a wonderful week. I'll see you in the consult.